Hey, hello Physical Science, this is Mr. B. We're going to finish up section 1 today with some examples of how to actually figure out how far distance and displacement actually are. We're going to have a little bit of simple math here today, so it's nothing going to be too difficult. So if you remember from the last video, distance is just how far something has actually traveled. So if you go 5 miles north, then you turn around and go 3 miles south, your total distance that you traveled is 8 miles. And then displacement, again, the definition that I think makes it a little bit easier to understand is just how far you are from your original starting point. So if you go 5 miles north and then turn around and you run 3 miles straight back south, your displacement is only 2 miles because you're only 2 miles from where you originally started from. And so now we're going to take a look at how we can add distance and how we can add displacement in terms of just figuring out again, how things are moving, because motion is the big overriding theme here. So we're going to add when we talk about displacements and distances, and we add them using vectors. So a vector is a quantity that has a magnitude and direction. So that sounds pretty confusing, I know, but I'm going to draw to you what a vector is to show you it's not that difficult. So all a vector is it is going to look like a line, and you know what, I'll make that so we can actually see it. If I can't make that any darker, there we go. Shape, black, and we will see if we can make it a little bit bigger. Oh, very good. So this right here is a line with an arrow pointing to it, and this is how vectors are represented. So this vector has a direction of pointing to the right, and then it also says it has a magnitude. So magnitude is just a number. So if I put insert text box 5 km, so for 5, so this vector saying that this whatever distance, so let's say your car, let's say you're driving in your car, this is saying that your car traveled 5 kilometers to the right, or if we want to get more specific, your car traveled 5 kilometers to the east. That is a vector. That's all it is. It is just a way to represent, again, magnitude, how far, and direction, which way they went. So if I took this and I moved it to make it look like that, now my vector is 5 kilometers to the north. Now if I turn it and move this way, it's 5 kilometers maybe to the northwest, things like that. So that's all a vector is. It's just a line that represents what direction and how far something moves. So displacement is an example of a vector. Again, arrows on a graph or map are used to represent the vectors, and the length of the arrow shows the magnitude of the vector, which is just what we saw. So technically, I could, again, if this was only 1 kilometer, maybe I would make it look like that. So the shorter the arrow, the shorter the actual distance is, but as long as you have a label associated with it, you can really probably make it as long as you need to, but that's just maybe a standard rule that, again, if you have a 1 kilometer vector compared to a 5 kilometer one, you would make the one that's only 1 kilometer shorter. And vector addition is just the combining of vector magnitudes and directions. So you can actually add these lines, and we're going to give a couple examples of the rules for adding the lines. So for our example, when two displacements represented by two vectors have the same direction, you can add their magnitudes. So if again, maybe if I can put in another one of those little lines here. So we'll put in this line, and then I gotta make it actually bigger so we can actually see it. Okay, so then if I have this vector, we'll copy and we'll make another one. So now we have two vectors right here. So when they're pointing in the same direction, we can add these two together. So if this one was 3 kilometers and this one was 5 kilometers, we would just take 3 plus 5. The total displacement there is now 8 kilometers. So it's pretty simple. Now, if these displacements were moving in opposite directions, so now if I have a displacement that looks like, or a vector that looks like this, Now, to figure out our total displacement, we would subtract. So we're going maybe 2 that way, and then we turn around, and maybe we go 5 that way. So that is, so if the arrows are pointing in opposite directions, we would subtract them. So we're going to go over a little example right here. So what this picture is showing us is that this car travels 4 kilometers to the east. It stops momentarily, then it travels 2 more kilometers to the east. So 4 kilometers plus 2 kilometers equals 6 kilometers. Pretty simple. So now I know this is a little bit confusing, but now what this picture is showing, that the car travels 4 kilometers to the east, and then it turns around and travels 2 kilometers back to the west. So now, instead of adding that 4 and the 2, we subtract it, because if you look, our vectors are pointing in opposite directions. So we went 4 this way, then we went 2 back that way, and now we're only 2 kilometers away from where we originally started. So that's all the vector addition is. It's pretty simple. I mean, we're going to do plenty of examples in class to actually figure this out, but that is how we can measure motion, with actually how far things travel. So again, this has a total distance of 6 kilometers. And now this car, if we were doing distances, this car, we would still add it. The car still traveled 4 kilometers this way, 2 kilometers. It still traveled a total distance of 6 miles, but its displacement is only 2. Or I'm sorry, kilometers. But its displacement is only 2 kilometers because it's only 2 kilometers away from where its original start point was. So that's the main difference between the distance and displacement there. And now, displacement isn't always going to be so simple to whereas we're just going to be able to measure a straight line. Sometimes we're going to have to use graphing to figure out what happens when there's multiple directions with our vectors. And there's something called the Pythagorean theorem, hopefully we all know what that is going to come very useful here for us in a little bit. So if you notice down here, so it's kind of small down here, we're going to follow the path that someone is going to take to school. So start, right here's his home, right here's his school. So you notice he's going to travel 1 block over to the east. Oh, wrong direction, sorry. Then he goes a block to the north, then he goes 2 more to the east, then he goes 3 more north to get to school. So he traveled a total of 1, 2, 3, 4, 5, 6, 7 blocks. So that was his distance. He physically walked 7 blocks to get to school. Now, we can do something to figure out the total displacement that's a little bit easier, and as hopefully you can maybe see right here, we're getting the formation of what looks like part of a right triangle. So we can draw what we call, this is going to be called a resultant vector. We can draw this line right here, and if we actually graph this out, we would find that he only actually traveled 5 total blocks. So if you remember from hopefully you guys have had some type of geometry, a 3, 4, 5 triangle. If you look, 1, 2, 3, 1, 2, 3, 4 blocks, and so this is going to, we automatically know that that is 5. So the Pythagorean theorem is a way we can figure out what his actual displacement was. So again, his distance was 7 blocks, but he is only 5. He only moved a net of 5. That's how far away he is from his ending point. So again, that sounds confusing, I know, but once we do examples in class, this will be a little more simpler. And this is just to wrap up what I just said. So the boy walked a total distance of 7 blocks. So that's what this, again, these yellow lines are how far he actually traveled. His distance, 1, 2, 3, 4, 5, 6, 7. The vector in red is called the resultant vector, which is the sum of 2 or more vectors. So if you look, this is a vector right here, this first block. This is another vector. This is another vector. This is another vector. So we added up all 4 of those vectors to get our resultant vector. And it points directly from the starting point to the ending point. So even though the boy walked 7 blocks himself, it was actually only 5 total blocks. But if you look, he's not going to cut through people's yards. He's not going to, again, just walk through random places. He's actually going to follow the street path. So that's why he traveled more than what his actual displacement was. So that is how, again, the difference between distance and displacement and how we can actually add it up and figure out. Again, we're going to do plenty of examples of those in class. But make sure if you have any questions, you write them down and you let me know.